Okay, so I got all my gear set up now. Do you have any questions about anything we've covered so far? Okay, so let's recap. You have one carbon with saturated with hydrogens. What do we call that? Hydrogens. Four hydrogens. Methane, 2 carbons. Ethane, 3. 4. Good. If I put a double bond in butane, what does it become? Butene. Good. And then I can change where the position of the bond is, and so we number that. Yeah. Left to right. All right. Good. And then, so there's 3 different kinds of isomers. Isomer means same parts. So, like, if I drew structural isomer on the test, would you be able to identify that? What kind of isomers are those? That's right. They're geometric. What is that one called specifically? Cis. This is trans. Good. Uh, and then the last one is optical isomers or enantiomers. Is that a optical isomer? Is that an optical isomer? Why? Right, and this one isn't because it only has how many? 3. Good. Excellent. And so, in biological systems, not medicine, we call the one that's the left-handed form, what's the... Well, the achiral means that it's not handed. So, they're chiral, but the left-handed one gets the designation L, and the right-handed one gets the designation D. And in medicine, the left-handed one gets the designation S, and the right-handed one gets the designation R. Good. So it has to do with the clockwise rotation around the chiral carbon center, but don't worry about it. I don't care that you know that. What I'm going to do is on the test, there'll be a picture like this, right? And I'll ask you, is that an optical isomer, an enantiomer, or not? So all you have to do is count the number of different bonds, groups on there, and then you should be able to tell me yes or no. So it's not going to be really hard. The reason that you need to learn this is because this is important in medicine, right? I think I gave you lots of examples of that. Other ones that we can talk about are, so for treatment of Parkinson's, they use DOPA. If you haven't seen the movie Awakenings, it's pretty good. It's kind of like about that. It's about people that got vaccinated in the 20s and 30s and developed Parkinson's-like symptoms. So in this case, DOPA has a right and a left-handed form, but only the left-handed form is biologically active. The right-handed form doesn't do anything at all. Prozac, it's the complete opposite. So here, Prozac the right-handed or D form is the one that's biologically active, and the left-handed form isn't. Okay, so I think you guys pretty much got it down. If you don't, it's just going to require some studying. Structural. So on the test, I might put first of all, what is that? Good. And so I might say that is isobutane. What kind of isomers are those? Structural. Right? To get it geometric, have a double bond in it, you can identify those right away. The other ones, the optical isomers, are of a carbon with this has the exact same group, right? This is the central carbon, and it has 1, 2, 3 identical groups. Those are called methyl, because the root is methane, right? CH4, and then this is just a hydrogen. So this only has 2 different. So would this be an optical isomer? The answer is no. Good question. All right, so just make sure you guys know the difference between the 3. And I'll put drawings on the test, so you'll need to be able to identify like I just did on the board. You don't have to memorize it, you just gotta look at the shape, right? So it's take a little practice. Yeah, so cis and trans is geometric. So the optical isomer would have a left and a right-handed form, so it would be an L and a D in biology, and an S and an R in medicine. Achiral, A means not, so that means it's not a chiral. Yeah, it doesn't. Chiral means handed, so achiral means it's not handed, so it's not an optical or not an optical isomer. The other word we use is enantiomer. It's the same. It means the same thing. Which one? So there's not. Those are different. So they don't. They're not. They wouldn't. They couldn't possibly ever be handed. So they would always be not handed. But we don't ever use that term in that respect, because they're just different kinds of molecules. All right. So think way back when to the second week of class when you guys were messing with these molecules and you had no idea what you were doing. So remember I asked you guys to look at the functional groups and record where they were found. So functional groups are important because they have to do with the reactions and most of this is about predicting reactions. What sort of thing is going to happen when you mix this with this? Is it going to blow up? Is it going to cure cancer? You need to be able to predict that. So we study functional groups, which are just small groups of atoms, usually bound to a carbon atom or attached to a carbon atom. Each of those have different physical and chemical properties, and we'll talk about those. They're usually the most reactive, and they usually impart the most functionality in living systems. So, just to give you an idea of how relevant this is, you guys pretty much know what testosterone is, right? So what happens if you have lots of testosterone? Let's say you're a female and you took your testosterone injections. What would happen? You get hairy, right? You probably get more muscular. So that is maleness traits, right? So testosterone produces maleness, and then estradiol is a precursor to estrogen. And you guys probably know what estrogen is. So if you were a guy and you took a lot of estrogen, like Meatloaf and Fight Club, yeah, so you would get female traits, right? Breasts, things like that. So these, we call these steroids, and they're fats. They're lipid steroids because they're carbons and hydrogens, right? Remember the difference between carbon and hydrogen? Carbon's 2.5, hydrogen's 2.1. So is that polar or nonpolar? Carbon's 2.5, hydrogen's 2.1. So what kind of bond is that? Polar or nonpolar? So will it dissolve in water? Yeah. No. So then we consider those fats, right? They're lipids. So these are lipid steroids. There's lots of different kinds. They're all synthesized off cholesterol, but the point that I'm trying to make here is that what's the difference between these two? Right, so there's not much difference. The difference are the functional groups, right? So this is a hydroxyl group, functional group. We're going to learn. You guys did learn it, but you probably forgot. Um, this is a CH3. What's that? Methyl group. And then anybody remember what this is? Well, it is an oxygen. Thanks. So that's a carbonyl, and specifically it's in between two carbon atoms. So this is what we call a ketone. Alright, so that's okay, we're going to learn them again. Um, let me just show you. We're gonna cover these again, but I just want to show you that there's lots of lipid steroids, and this is one area that I did a lot of research on because you guys probably know the correlation between cholesterol and cardiovascular disease. So what? So do you think that having a high cholesterol has an effect on your risk of heart attack? You're wrong. Doesn't matter. So there's a Framingham study that's been going on for about almost 100 years now, and it's to take a group of people that have naturally high cholesterol, naturally high LDL, and a group of people that have naturally low LDL, and they followed them and looked at their risk, their incidence of cardiovascular events, stroke, heart disease, heart attacks. What do you think the difference is between those two groups? They're exactly the same. So, what does that tell you? You've been tricked by the pharmaceutical companies to think that's a fact.
But you just said they have naturally high cholesterol or low cholesterol,
Right.
not necessarily from
Okay, so here's another fact, a fun fact, is that 80% of the people in this room, it wouldn't matter what you ate. You could eat greasy cheeseburgers all day and night, and it wouldn't change your cholesterol level. You know that? Because your body wants to maintain homeostasis. So your liver processes that out. Only a very small percent of people can, their diet would affect their cholesterol level. Well, that does insulin regulation, but not your cholesterol levels. That's produced by the liver.
Doesn't all those three factors combine to sum up the coronary artery disease?
So why take cholesterol medication?
That's a great question. Why?
So nobody in the world needs cholesterol medication.
Okay, so I can tell you for a fact, I've done research for 10 years on cardiovascular disease, that you will never find a study that shows that if you look at LDL levels and people with high LDL, that they would increase their risk of getting heart disease than someone that had low LDL.
So what does cholesterol do? Doesn't it build up and then it creates clots? So
Yeah, so this is how it works.
like
I wasn't prepared to go down this path, but since we've already started down this,
kind of have
let's just carry on here. So here's an artery. Your artery's made of smooth muscle, and that's made out of cells. And in your blood, you have things called monocytes. They're white blood cells. They're kind of white blood cell, and they just cruise around and they don't really do much. Their job is to look for like something wrong, some sort of foreign invader, bacteria, something bad. And once they detect that, and the smooth muscle cells can produce these things called cytokines or chemokines. They're just chemical compounds that excites these things, and they will start binding to this. So your blood's flowing pretty good, right? So it's like rolling a bowling ball and then covering it with Velcro and rolling it on a carpet. So these things slow it down, and then it will once it binds here, it will turn into what we call a macrophage, and then those will squirm in between to look for like an inflammation or something like that. If it doesn't find it, or even if it does, it will start digesting it. But one of the issues is that one of the things it will also take in is LDL. And the reason that LDL can get in here is because it's low density. So what do you think the difference between low density and high density is? Which one do you think is bigger? Yeah, so high density ones can't fit in between the cells. So it doesn't get into the artery wall. LDL and VLDL, which is another kind that you probably never heard of, can get in here, and the macrophages will eat it.
So what does someone use to control these receptors?
So cholesterol medication, your cholesterol medication messes with your homeostasis. You need cholesterol because without it, you couldn't make testosterone or estrogen. You couldn't make any of these. All these chemicals are all cholesterol-based compounds. I mean, you could see if you look at
so basically we're killing ourselves by taking cholesterol.
list of all these.
There's wash their hands.
So this is a real factor, right? But it's the same as saying, okay, well, ice cream consumption increases in the summer and so does drownings, right? Because LDL is always going to be there. If you lower your LDL, your body will synthesize more, right? So this is going to happen anyway. Well, what causes it to begin with is inflammation. So that's why there's a real correlation between like gum disease and plaques. And so these things will gorge themselves and they get really fat and they start pushing on the vessel walls and they pinch off. Right? And so that's what causes cardiovascular disease. It's inflammation, not your cholesterol level. However, and I don't know if you guys know this or not, but if you look at the old commercials for like Lipitor, those statins that reduce your cholesterol level, they had to put a disclaimer on there that said there's no correlation between heart disease and cholesterol level. However, Pfizer did a study, they funded this study, and what it found is that there was a small significant difference between people that took Lipitor and people that didn't in cardiovascular events, right? So that would lead you to believe that lowering the LDL cholesterol prevented cardiovascular disease, right? But statins, those drugs, they have a bigger effect on inflammation like aspirin does. So what is really inhibiting that isn't the cholesterol level, it's anti-inflammatories. And so here's another fun fact. If you take a statin, I'm not telling you shouldn't take the statin, right? But if you take a statin, it helps 1 out of 100 people with this because it reduces the inflammation. But 4 out of 100 people will develop cancer from taking statins.
What is the person?
I'm not sure.
What kind of cancer? Leukemia?
I'm not sure. Probably lymphomas. So, you have to ask yourself, what would you rather have, cardiovascular disease or cancer? So, anyway, sorry. And you know what started this all is that someone did a study on rats, kind of like that saccharin study where they fed the rats saccharin and they got cancer. You remember that? But they were feeding them like 5 times their body weight. So it was like, who's going to eat 500 pounds of saccharin in one sitting? Nobody, no human. So it really isn't relevant. And then people started freaking out about the cholesterol, right? So they identified it as practicing bad medicine if you had a patient that came in and had high cholesterol if you didn't prescribe a statin. And that's still in effect today. Doctors can get fired if you're in a hospital setting or reprimanded for not prescribing a statin. That
It should actually be more harmful to you.
right, because they believe that it's preventative medicine.
But they've all taken biology.
Huh?
1%.
So yeah, but a lot of them don't.
Like if I was given this information as a patient and the doctor then tried to prescribe me statin, I would probably throw something out of the office.
Well, I mean, you shouldn't throw stuff. Maybe you should discuss it. But I'm just telling you. I mean, you guys, you can't go around blindly just thinking, trusting stuff. Like mom says, washing your hands does junk, because we all know now that it doesn't, right?
Art did.
Well, most people it doesn't. You really have to scrub in like a surgeon to make it effective. Hand sanitizer is a lot more effective. If you guys use that, you'd see that there's nothing that grew. There would be nothing. So that's what I use all the time. I do wash my hands, and they're dirty, but not to get rid of bacteria.
I'm pretty fascinated with misconceptions like this.
Yeah.
What's your take on when kids are like given sweets, whether or not it really causes them to be hyperactive?
So, I mean, it can, because it increases your ability to produce energy, because it's an immediate thing. Yeah, and then you could have crashes. It's better to have a consistent level of blood sugar, even when you're an adult, right? Because your body thinks it's starving, and so it makes you want to eat more. But I'm not like an expert on that sort of thing because I didn't really study it. So you should look it up. That's my point. Yeah.
A lot of it says it's a misconception. It's just like mothers passing down, take this soda.
Right, or don't make sure you don't go swimming for 30 minutes after you, yeah, because you'll get a cramp or something, you're gonna drown. Yeah, so I don't know where this stuff comes from, but I mean it's definitely, I want you guys to think like scientists. So question everything, right? Even, I mean, if you're taking medication, you should know what it does, how it works, if it helps people or not, because in reality, you know what the most money that was made off of any drug last year was? It was a statin, right? It was Lipitor. That made Pfizer $10 billion. So would you want to give that up? Would you want to let the cat out of the bag and go around telling people, hey, this really doesn't do anything? So, but you know what? pharmaceutical reps, their budgets are like $100,000. They go in and they buy like platters for doctors and take them on golf outings. Do you think they want that to stop? Man, when I worked at the VA, they would take us out. We were in this endocrinology society, right? I don't know if we had a secret handshake or something. I never learned. But every week, the pharmaceutical companies would take us out to, McCormick and Smith's, and they'd give you a little like 5-minute presentation. Why do you think most people showed up to that? Right. So if you like stop prescribing their medication, what are they going to do? Yeah, and if they don't make as much money, then you don't get that free weekend golfing trip to Palm Springs or whatever. So it's almost kind of a scam.
I work at a neurologist's office, and there's a different drug rep every day offering us lunch.
Yeah, because they want the doctors to write the scripts for their medication. Why else would they be there? Okay, back on track. Question. I think they just don't know. I think that like most doctors don't know. I think that if you talk to someone that had a lot more knowledge in like a thoracic or a cardiovascular surgeon or something like that, they know, and they're gonna be like, because they put in these stents, right? I mean, they make bank doing that.
$50,000.
Yeah. Yeah. So yeah, let's move on. We'll save that for another side discussion. Okay, so the functional groups you're just going to have to memorize. There's 6 of them that are biologically important, but believe me, there's lots more. Well, there's actually 7, but I assume you guys already know the methane group or the methyl group, which is CH3. So the hydroxyl group is simply an OH, and so here's a good example. So if there was just an H there, what molecule would this be? Where that blue is highlighted, it's just an H. Ethane. So when we put an OH on the end, that makes it an alcohol. So now it's an alcohol's end in OE, right? The word alcohol. So it's ethane all. Right. Well, I mean, yeah, just for that particular functional group. So things can get really complicated really fast. I mean, you could have molecules with tons and tons of functional groups. So So this is pretty basic stuff. I don't want you to universalize this. We're just going to keep it to the basics for this class. When you take organic chemistry, then you'll learn all this other junk. No, probably not. I didn't really like organic chemistry either. So, carbonyl groups, they're a C double bond to an O, and so if it ends on the end of a molecule, you have to add a hydrogen there, right? Because carbon has to have 4 bonds. So on the end of a molecule, it's C double bond O and an H, and we call that an aldehyde. If it's in the middle, you don't have to put a hydrogen on it, right? Because it's already got its 4 bonds. So we call that a ketone. So back to this, what is that? It's a ketone because it's in the middle, right? If it was on the end, what would it be? Well, they're both carbonyls. Yeah, that's right. The end of the molecule. So this is an aldehyde because it's on the end. Right? This is a ketone because it's in the middle. Did you see that? Alright. The reason I'm showing you this, I'm just going to jump ahead really quick and we'll come back to it, but so in the next chapter we're going to talk about sugars. And so, and we'll talk about this again, but there are certain sugars that are called aldoses because they have aldehyde groups, right? So ribose is one. Where do we find that sugar? DNA and RNA. Glucose, where would you find that? Well, yeah, that's part of it. Yeah, so it's glucose and fructose. So, right, but yeah, it's carbohydrates, right? Long chains of glucose, and then these are ketoses, right? So, this is fructose. If you counted up the carbons, you would see it's the same. This and this are the same.
Because it's in the middle of ketosis.
This is a ketone. This is an aldehyde. These are the exact same. These are isomers, right? Because they have the same number of parts, different arrangement. And I'm not going to make you guess this right now, but when we get to chapter 5, I'll show you why they're different. But that's why you need to know that. Any questions about these? Alright, so like I said, it's going to take memorizations on your part, so you're just going to have to sit down with some flashcards or whatever. So this one is a carboxyl because it's C double bond to an O and then another oxygen, and then obviously that oxygen needs two bonds, so it's a hydrogen. So it's C double bond O OH. It's on the end of the molecule, like so. If it's inside, it becomes an ester, but we'll talk about that later. Let's just focus on this one now. So, what's an ion? It's a charged molecule. So, remember oxygen and hydrogen, they don't share very well. So you have this molecule, like so, and these are sharing electrons fine. But oxygen that sometimes forgets to share with hydrogen, and what happens to it then? It can't make the covalent bond anymore. So it leaves without the electron that oxygen took. So this becomes H plus, and then this becomes O minus. Does that make sense? So carboxyl groups are also called acids or carboxylic acids. Why is that? What's the definition of an acid?
pH levels lower than 7. So
Okay, but what makes it lower than 7? What about the H pluses? Are they more?
H plus and the OH.
Okay, but an acid is something that, by definition, donates H pluses into the solution. So what's this doing?
H plus.
So then that, by definition, is an acid, right? So, everybody get it? All right. So here's an example of this. The base part of this is ethane, but when you put a carboxyl group on the end, it becomes an acid. This is acetic acid, which is a weak acid. In fact, the other term for that is vinegar.
So more carbon bonds with a carboxyl, the higher the acidity.
Yeah, but it's always going to be on the end of the molecule, so yeah, I mean, you could have a bunch of carboxyls if you had it would be more acidic. Yes. That answer your question, yes. Any other ones? Okay, so amino groups. Remember we talked about amino acids, and you guys should be familiar with these. So they have carboxylic acid on one end, and on the other end they have NH2. This is the amino. That's where they get the name amino acid. And then this is the variable group. And there's 20 different ones. So let's focus on the amino remember when you guys were messing with nitrogen, the blue molecules? So if you looked at nitrogen, what would you predict its valence is? 3, so how many bonds should it form? Sometimes it gets a little weird, right? Because it's on that cusp of like, it could gain 3 and make it shell full, or it could lose 5 and make it shell full. So sometimes it will take on extra bonds that it can't possibly maintain for very long. So this is an example of this. So nitrogen has how many bonds here? But it can transiently pull in a hydrogen that the H plus is by itself, so then it becomes a plus charge, right? So what do we call something that pulls hydrogens out of a solution? It's a base. So this is a base and that's an acid. In fact, sometimes this hydrogen will come off of here and go back over here, and then they play this little game of going back and forth on amino acids. It's like hot potato but with hydrogen. Sure. So let's do it on the screen. So here's amino group. So we have a carbon bound here, or something, some other chain. This one, the nitrogen has the 3 bonds to make it neutral, but sometimes it can pick up an extra hydrogen, so it will pull it out of the solution and make, instead of NH2, this is NH3 with a charge. And because it takes it out of solution, by definition, an amino group is a base.
When the hydrogen comes back.
Yeah. So we call things that have a dual nature like this amphipathic. That's the word of the day. Go home and use it in a sentence. Amphipathic. So the second to last group is what we call the sulfhydryl groups. These are usually found in proteins. They're very, very, very strong bonds, right? You can think of it as like the diamonds of the chemical world. So they're hard to break. They help make the structure more rigid. And these are commonly found in certain kinds of proteins. So you guys have a protein inside your mouth called amylase, and what it does is it breaks down starches, so long chains of glucoses, and that produces maltose. So you could go home and put a cracker in your mouth and let it sit for a while, and it would start to taste like a Whopper, because that's the kind of sugar that it would make, right? The malted sugar. So that enzyme is also exposed to, does everybody drink the same temperature drink? So what happens when you drink a hot drink? What does that do to proteins? It changes their shape, right? It's like frying an egg, we talked about that. Or you drink a cold drink, what would it do? Change its shape. So like you'd be putting all kinds of stuff in your mouth, and that enzyme wouldn't work half the time because it wouldn't be at a specific temperature. So how do you make it not change its shape? Give it strong bonds, like disulfide bonds. Okay. That's not true for all proteins. Proteins that are inside your cell, they're not going to be exposed to all these different temperatures and different pHs, right? So they don't need a lot of sulfur bonds. Does that make sense? You also have an enzyme in your eye that its job is to, it's called a lysozyme. Anybody want to guess what it does? Why you have it there? Okay. What stuff would you get in your eye? Yeah, but who cares about dust and dirt? What would be more? Yeah. So it breaks down bacterial cell walls that float into your eye. That's a really good way to get inside you. It's hard to get through your mouth and stuff because your stomach acid would destroy them, but they can get in through your eyes pretty easily. So without that enzyme, you get a lot of bacterial infections in your eye. And so you go outside at different temperatures, right? So would you like that enzyme to stop working when you go outside and it's chilly? or hot. So can you guess, does that have a lot of sulfur bonds or not? Yeah. So that, and one thing that we're going to talk about later, how they discovered that DNA was the genetic material, is that sulfur is only found in proteins, not DNA. DNA doesn't contain sulfur. So just remember that. Any questions about sulfhydryl bonds? So these are strong bonds. What are they used for if I ask you on a test? Maintaining shape, yeah, exactly. What's the most important thing in biology? Yeah. Indirectly, yeah, it's shape. What can change shape? Two things: temperature and pH. Yeah. So those are the two most important things that we have to maintain our structures, our protein structures. All right, last one is the phosphate group. And you guys probably don't remember this from the lab, but I asked you to do this, look at these two, and so I'm going to draw the molecule. Okay, so this is called a nucleotide. It consists of three parts. One is the base. This is the sugar. And this is the phosphate group. So this together, all three of those, is called the nucleotide. What sugar is that? Close. No? Ribose, good. How do you know it's ribose? Yeah, it has an OH here, right? If I take away the oxygen, what is it called then? So ribose is RNA and deoxyribose is DNA. These vary, right? They can be single ring or double ring. You guys looked at the cytosine and the guanine ones in lab. And then this is a phosphate group. So what's the charge on DNA? Does it have a charge? Okay, so there's only three options: positive, negative, neutral. Anyone want to guess? So what is on the screen? What is that? Functional group. It's negative, right? So DNA has a phosphate group. So what's the charge on DNA? It's negative, right? Because phosphates are negative, so DNA is negatively charged. So, you know, whenever you watch like Maury or Jerry Springer or whatever, and they want to find out who the baby's daddy is, they put the DNA in an electric field and they separate it out. So which direction do you think the DNA goes to? The positive end or the negative end? Positive end. You guys are going to do this in lab. Right? You're going to do this before then, but you guys will all do this in lab, and you're going to take your DNA out of your mouth and we'll do DNA fingerprinting. And the reason we can do that, the reason that Maury can find out who the reason Maury has a show, right, because he wouldn't have one otherwise, he didn't have that little magic envelope, is because of the charge on DNA. Right? So it's important that you keep that in mind. I think that's all I have to say about this. One other thing is that DNA, phosphate phosphate is only found in DNA. It's not found in proteins. So that's another sort of foreshadowing that we're going to talk about when we get to chapter 13 and 14. All right, so remember the big six of the molecules. What are the most common ones? Carbon, oxygen, hydrogen, nitrogen, phosphorus, sulfur. Where's phosphorus found? Why is it so important? DNA, right? You put fertilizer in the soil for plants. Why do you do that? And phosphorus, because it can't get that from the air, right? It's taking carbon dioxide out of the air and building sugars, but it can't use that to build DNA, and it can't use that to build proteins, right? It needs sulfur to build proteins. Any questions about chapter 4? It's basically just a lot of memorization, but it'll be important later on. So don't think that you can just blow it off and not learn this stuff, because you're gonna be completely lost as we go along. Chapter 5. This is the last chapter, by the way, that's going to be on your test, which you guys will take on October the 2nd. So you'll need a green Scantron. You can get it from the bookstore. You might as well buy 4, because that's how many tests you're going to have in here. You'll need a number 2 pencil, so don't take the test in pen. That like super pisses me off. And then you can bring a periodic table. So you can just Google, just go to Google Images and type in periodic table and print out one. I'm not going to cover that up, but it's hard to see on this side of the room, especially the numbers. So you can bring your own. You can bring a calculator. The only rule is that it can't be graphing, and it can't be programmable, and it can't be linked to any sort of device that could be connected to the internet. So that means no phone, no iPad, no. So, I got my non-programmable, non-graphing calculator at the dollar store. Guess what I paid? You can, as long as it doesn't graph or you can't program it. So like a 35 or whatever, you can't. That's fine. Just keeping you guys honest. All right. So this chapter deals with all the different kinds of molecules we call macromolecules. So we started off with atoms, right? And then we're dealing with small molecules like water and functional groups. Now we're going to talk about bigger molecules. These are the ones that you guys built in the lab. So do you remember what you built? So you built glucose, and then you linked it together, and what did you call that? You're right. It's amylose is the word, and so yeah, carbohydrates. What else did you build? Triglycerides. Yes. So glycerol and 3 fatty acids. So that's the fat. That's how we store our energy as animals. What else did you build? That you didn't build. I mean, you did, but that's not a macromolecule. That's just a side product of building the macromolecules. So you built amino acids and you put them together. What does that make? What are long chains of amino acids called? Proteins, yeah. So those are macromolecules, right? fats are macromolecules, carbs, amylose, carbohydrates are macromolecules, proteins are macromolecules. This is, we link, DNA wouldn't do much good if it was just one letter, right? So you have to link them all together. And so that's macromolecules too. So we add nucleotides and long chains. And then same thing with RNA. So all those are biologically important large molecules, and they all have one thing in common. They're all built from smaller parts. So the individual parts, like the amino acids and proteins, or the glucose molecules and carbohydrates, or the nucleotides in the long chains of DNA, those we call monomers, right? Mono means what? One, and poly means many. And sometimes they're called dimers, which is two. So, everybody get the difference between monomer and polymer? Okay. So, you guys did this in the chemistry lab, and so you know that when you put two molecules together, what'd you have to do to make those work? So you had to take out water, and it's the opposite of hydrolysis. Yeah, if you run out of water, you're dehydrated. So that's a dehydration reaction. Doesn't matter what you're making. If you're making polyester pants, you got to still do the same thing. And then hydrolysis is the opposite. So if you add water, it breaks molecules down. So, we talked a little bit about this in lab, but if you were collecting DNA at a crime lab, and we talked a little bit of this about how we store pieces of DNA we need to use to copy it. Do you think we store them in water, in large amounts of water, or in smallest amounts? Yeah. So because if you store it in water, what happens? It breaks down, right? So, and then we talked a little bit about where life formed, right? You guys probably have them. I don't want to ruin anyone's, misnomers again for like the second time tonight, but you probably heard that, life probably started in the ocean or whatever, but that can't be true. Why? Yeah, you'd never be able to get the long strands of DNA to form together in the presence of water. So that could never happen. I don't profess to know where, how this happened or anything, but I know that's not possible. Just like I know time travel isn't possible. Did I ruin anyone else's night? Probably Stephen Hawking. Or if you're watching Stephen, I'm sorry. It's not. You can't do it. But check out the second law of thermodynamics. That's why.
You know what? It probably will be possible, like in a billion years.
Do you guys know? You know what I'm talking about? Did I tell you the story about this?
Yeah, the cards, the invitation.
Right. So that's Stephen Hawking. All right. So macromolecules, you guys probably know these from your nutritional label. We got carbohydrates, right, and then lipids or fats, right, on your nutritional label, and then proteins. All those we use as an energy source, and it gets broken down in a similar fashion, but it's still different. The body processes it differently. I told the other class, it's kind of like me. If I said I'm going to Flagstaff, I wouldn't have to take one specific route, right? I could take lots of different routes and still get to the same place. That's how your body processes these things. So it breaks them up, it puts them in the reactions in different ways, and then in the end, doesn't matter which way you get there, you're still going to end up with not Flagstaff, but what's our ultimate goal here? To make ATP, yeah, our energy source. So, and then nucleic acids, we can't use those as an energy source, but we still need them, right, to make DNA. So here's a question. We're mammals, right? So we all, nobody came out of the womb eating steak and potatoes or whatever, right? We all fed off of milk. Do you think milk has DNA in it? Okay, where would that DNA come from then? Okay. I hate to tell you, but cows and humans make milk the same way, right? Yeah. So it's the same way you make saliva. It's a gland, right? And it has cells around it, and those cells export certain things, right? So if you look at the nutritional label in milk, it has fat, right? You could buy it with, it taken off, but we're just talking about regular milk, right? And then it has protein in it, and it also has sugars. But the question is, does it have DNA? These cells are making this and putting it out. So, how many copies of DNA does this cell have? Well, complete set. 1. So if it took its DNA and chucked it out into the milk, what would happen to the cell? It would die. So, do you think milk has DNA in it? Okay, so now let's ask another question. All of us know
It's
that.
called lactation. Lactase,
Well, that has to do with a cow. That's the term for a cow. But okay, so we have cells. So we have cells.
that cell is doing
No,
this.
I'm not doing this, right? I'm doing this. Cells, right? So we have cells and they're dividing. And when a cell divides, everybody came from a single cell. And then you were born, so you went from one cell to trillions of cells. That means you had to copy your DNA, right? But you're only getting this. So how do you get DNA?
You're born with all you need.
You're a single cell.
That's what you're.
Well, what? DNA requires fat, proteins, and carbs to grow, right?
Okay, so after you're born, right, you're going to feed on milk and you're going to grow. That means your cells have to divide.
But you already had the DNA in that one single cell.
Right. So, okay, so let's say your cells are dividing when you're growing up from a baby. Does everybody trust that's true? That means you're making new cells, right? That means if you're making an identical cell, you have to copy the DNA. It's like paper in a copy machine. You can't just magically get copies out of endless with reams of magical paper. So the question is, how do we get DNA if this is what we grew up on? Yeah, nucleic acids, exactly. Where do they come from? You eat your mom? Your body makes it. From what? No, your body makes it from this, right? It rearranges these things in such a way where you can use proteins, carbs, and fats, just like Legos, to rebuild the nucleotides. So you're synthesizing your own DNA. You're not taking it in. Does that make sense?
So I'm gonna tell you what I'm confused on.
Okay.
Because everybody has their own DNA markers.
Right?
So let's say my daughter, for instance, she has her own DNA. Is her body changing those into her DNA?
Yeah. So, I mean, it's like,
But she's not getting DNA from my wife saying, she's not getting Carly's DNA because
so you have to think about, this is nucleotides, right? Not strands. You can rearrange them in any way you want. So your body's going to synthesize the letters that it needs and put them in that order. It's like if I bought a set, like a magnetic letter set that my kid has to put on the refrigerator. It's not like I can only make the word A, B, C, D, E, F, G. I can rearrange it however I want, but I still need the parts. Does that make sense? Whew. All right. forget it. I don't want to go down another tangent. Okay. On. Okay. So,
nucleic acid, right?
yes,
What is their molecular structure?
it's right there. Oh, it's not anymore. I erased it.
Oh, that thing. Right here. Got it.
Here. So this will be at the end of this chapter.
Phosphates and adenine.
But this is what it looks like. This is a nucleic acid. Nitrogenous base, pentose sugar, phosphate group. These are the different bases, right? And then this is the difference between DNA and RNA. It's the sugar. This is the DNA strands built together. But that's for another lecture. So let's go back. We're going to start with carbohydrates, right? So carbohydrates are built with sugars, the monomers that are sugars, and we can name and describe carbohydrates differently based on the type of sugars that build them. So we have monomers, we link them into long chains, we make polymers. The monomers of carbohydrates we call monosaccharides, right? And then sometimes those are called simple sugars. And then we link them together and we can make two sugars. So what do you think that's called? So disaccharide, and then generally if it's three or more, it's polysaccharides. Good. So examples of this are fructose, glucose, lactose. I showed you guys the pictures of those earlier, and we'll get to those again in a second. So when we build these molecules together, what's the reaction to put them together? Other one, dehydration. Take water out, build the molecules together. So when we build these, we call them complex carbs, right? Or complex sugars. Starches, like carbohydrates, like are in your Doritos and stuff. And then fiber. So believe it or not, fiber, like cellulose, right? It ends in OSE, so what do you think it is? It's a sugar. So another kind of carbohydrate is fiber, right? Which is what we call cellulose. And that's listed in your nutritional label under sugars, even though it's not digestible. Alright, so monosaccharides are sugars because usually they come in a 1 to 2 to 1 ratio, right? So it's a 1 carbon, 2 hydrogen, 1 oxygen. So like C6H12O6. That's a classic molecular formula for sugar. Sugars end in OSE, you guys know that, I think. Glucose is the most common and the easiest one for your body to utilize. So your body loves glucose. It can process it just like that, right? All the other sugars are hard to process. And your body will preferentially use glucose over anything else that's available if it has it available to it. Remember that when you're taking in glucose, so plants are building it up, right? As they're doing photosynthesis, they're making glucose and they're linking it together in long chains, and they're storing it as a carbohydrate. And then at night, they can't just use the sun as an energy source because at night they would die. So they use the stored carbohydrates the same way you would. They eat them, they don't literally eat them, but they digest them, and then they release ATP energy. But you guys sneak up on them and take their carbohydrates and use it for yourself. Selfish. So, just kidding. So that's what we do. That's how we'll break down the sugars. So this chapter is just discussing how we break them into monosaccharides. And then later on in chapter 9, we'll talk about how those monosaccharides become ATP. Alright. So monosaccharides have a carbonyl group and hydroxyl groups. If the carbonyl group is at the end, what do we call it? It's an aldehyde, but because it's a sugar, we use the word OSE, so it's an aldose. And then if it's a carbonyl group that's in the middle, it's a ketone, but because it's in a sugar, we call it a ketose. Fructose is a ketose, glucose is an aldose. These are structural isomers of one another. And then we also name sugars by the number of carbons they have. So glucose is C6, you guys know that. So what's the shape? I watch a lot of this because I have a kindergartner. Yeah, hexagon, good. And then if it has 5 carbons in it, what would that be? A pentose, right? And you have, 8 carbon sugars, and then 3 triose. So you guys get it, good. So here's triose sugars. Glyceraldehyde is one. Dihydroxyacetone is one. These are aldoses because this is just what I showed you. They're on the end. These are ketoses because the ketone group, the carbonyl group, is in the middle. Here's glucose and galactose. These are very closely related to one another. In fact, you would think these are the same because I told you that bond would rotate, right? But they don't normally follow this sort of structure. What they do is they form rings, like so. So in this case, you have this molecule which has an OH here in this ring. So if I had sticks and I shoved them at an angle, so if I had 2 sticks and I stuck it in an orange, I could spin that orange if the sticks were straight. But if I stuck them in at an angle, could you spin the orange? No. So in a ring structure, this group right here can't rotate, and that's what makes them different. So we'll talk about that later on. We'll end the session. Unless you guys want to argue about stat. Hey, if you guys are taking a stat, don't stop taking it till you talk to your doctor. I'm not a medical professional.
Oh, yeah.
Yeah, because it inhibits clotting when you have artificial things put in your body.